Okay, good morning. Good morning, Thomas. Good morning, everyone. I think because I was just writing to my colleague, it seems that there are not a lot of people, but one of them is just connected to the whole class. Mikkel, are you there? And the whole class is just with one camera. So I think that we can start. Good morning again. Thank you so much, Thomas. I have the great honor just to introduce Professor Thomas Vilgis. He's a great scientist. He had quite a lot of connections with gastronomy, quite a lot of works with different chefs. His expertise is in soft matter and food physics, physical chemistry. And today he will talk about the relation between the physics and the mouthfeel. Good morning, Thomas.
Good morning, Juan Carlos, and thank you very much for inviting me. It's for me a great honor to speak in the Basque Culinary Center, which is worldwide known and has the best reputation ever. And I'm really happy to speak today. And I would like to talk about soft and hard emulsions, because this is something which is just a sort of an example of a soft matter system, which is simple enough, but as you will see, complicated as well. So this is our institute, what you see here. So I'm working, we have a laboratory, we have some laboratories here and in this building, and we try to use the whole soft matter methods which are located in this institute, just to understand food, at least a little bit from a physics point of view. Now, emulsions are everywhere. This is a typical plate from a German two-star chef, which is different textures, and you see some creams, some emulsions everywhere, some gels, some liquid gels, some fluid gels, some vegetables, some flowers. Beautiful. And this is, of course, which makes the good mouthfeel and the different in textures, which gives us pleasure as guests and as eaters, and to enjoy this plate completely. And I have to dive into this emulsions, because what we do with the mouth is oral processing, and we have this soft matter in the mouth, and depending on the texture, depending on the structure, depending on the physics, we have to chew it, we have to squeeze it, we have to oral process it before we swallow it. And during this oral processing, we get all the pleasures of taste, aroma, texture, flavors, everything, sensations, which builds our brain together in with our cultural and our background and our biography, what we have eaten during our lives. Now the apparatus, mouth, the tongue and the palate, it's one of the most sensitive materials testing device. As you all know from eating chocolate, if you put chocolate with 20 degrees in the mouth, it melts and it releases everything. And if the chocolate is perfect, it melts at 33.8 degrees Celsius. And when it's not perfect, it melts at different temperatures. You feel it immediately, and you think this chocolate is not correct chocolate, or this is something else, and something went wrong during preparation and during the preparation of the chocolate. And so you feel a lot of things in your mouth, and this is quite sensitive, what I wanted to say. Food perception is indeed a multi-scale. Because if you look at this graphs, and because it covers length scales from angstroms, from atomistic length scales, from 0.1 nanometers up to millimeters and centimeters, and when you see what molecules play a role, of course there is always water, there is always oil. This is in the range of very, very small scales, glucose, fructose, which give taste, for example, aroma compounds. Then in the 10 to 100 nanometers, we have all these hydrocolloids, proteins, and there are also somewhere emulsion droplets, We feel the grains in the starch when they become larger than 10 micrometers. We see foam bubbles, which are micrometers as well, and the macroscopic foods are macroscopic, or the macroscopic foods have all distant or all length scales between centimeters and millimeters. And so what we can see is, from this we can really classify the food along these length scales, because the taste and flavors are released in small scales. Small scales play a role. We feel the structure by the texture, or we feel the structure which is built up by structure-giving molecules like proteins, hydrocolloids in milk, for example, casi in micelles, or emulsion droplets, fat droplets in soy milk, oleosomes and things like that. And later on, we feel the texture built up from this structure. So food perception is a complicated subject to study, and this is why I'm a physicist, as a simple-minded physicist, is really interested in that as well, because A, it's complicated, and B, it has multi-scales, and we have to think in lots of different measurements and lots of different theories. So why are emulsions so desired systems? Of course, a glass of milk is by its own a sensation. Aioli and all these nice mayonnaises are really something quite nice. Butter is an inverse emulsion, what this we will realize later. It's also some quite nice stuff, but also creams and chocolate creams and are typical components for sweets and things like that. So I just have put a little bit, just the most simplest and most well-known examples here, without going too much into the detail of modern gastronomy. Now, the basic problem what we see is that all these things consist of oil and water to some extent, apart from the flavors. And the basic problems between oil and water is that it's not miscible. Well, this is a simple experiment. You color some water with a dye, and you put some oil on it, and you see there are interfaces. It's a clear interface after some time. And you see, if you do molecular simulations, then you see this interfaces, it goes down to the scale of molecules. So this is really a good indication that fat molecules, here a simple model, there's a role and 3 fatty acids. It doesn't mix with water molecule H2O, and which is polar, which has dipole. This doesn't have a dipole, and this is a simple physical reasons why these 2 molecules do not mix even on molecular scales. So there is an interface between oil and water, and this is quite interesting because it has a deeper sense in this emulsions, because in this fats, the fat is the perfect solvent, the good solvent for most of the aroma compounds, basically for all aroma compounds. So for all volatile aroma compounds, they dissolve in fat, and all in water, all taste relevant molecules dissolve in water, because salt, sugars, glutamate for umami, and some bitter components in tea, for example, acids, they dissolve in water. So there is a clear separation for the flavor, different flavors in taste and aromas, taste and smells, which dissolve in different solvents. And this is why also emulsions are a perfect system to study also flavor release. And this is why I have chosen the subject for today for this lecture. Emulsions have other very quite nice properties. They are ruled by interfaces, and they have a different structure and dynamics, and this makes it very sensational. They are droplets, most oil droplets, and this is just an artistic photograph where the oil droplets have different colors. This is normally not the case, except if you do it like that. There's a water phase, and there's a water phase here. There are droplets, and they are separated by interfaces. And these interfaces make a lot of physics, make a lot of dynamics, and make a lot of flavor release. And everything is ruled by the interfaces, and this we are going to study. There is, of course, the problem of stability. Emulsions, this is a very simple picture. This is in German, excuse me, but I will explain. There are droplets inside, the oil droplets inside water. This is a very simple emulsion. And you can have even flocculation, so they lump together to some bigger droplets. Eventually, there is coalescence, and then they become bigger droplets, and the emulsion is not stable anymore. So the other one, even if they bump together by some dynamics, they will form, they will demix, and they will oil layer on top, and the water is on the here on the bottom. Or there is some creaming, like we know from milk, from raw milk, from non-pasteurized milk. There is always some nice creaming, and the cream, the fat layer on top, it has really nice properties from the mouthfeel, and this is what happens here. So there are many different things, and the crucial thing is also for gastronomic properties, for gastronomic applications, how to stabilize the emulsions. They are just to give a feeling what will you expect in this lecture is. This is a classical aioli, just egg oil beaten with garlic and all sorts of nice spices, but it forms droplets. If you look at it in microscopy, it forms droplets. There are some small droplets squeezed in here, but there is a waterish phase. The water comes from the egg yolk. But what it basically says is that these droplets, they really can't move. This is drawn here in this cartoon. These droplets, forget about the shape, it's just droplets. And they are here sitting in a cage, surrounded by a cage. The cage is produced by the other molecules, and they are just stuck in the cage. They are, so to speak, like in a traffic jam, so where they are jammed in this cage, and they can't escape from this cage, except if one makes place, and then it can escape. But this is caged as well, surrounded with other droplets. So this is something which determines the texture and the mouthfeel of some these emulsions. And the better this cage, the closer this cage is locked, the better is the creaminess or whatsoever. So we have some examples for this, because milk is an emulsion. It's an oil in water emulsion, so it's milk fat inside droplets in this way. And this is very liquid, so the droplets are separated, and this mayonnaise here, they are just caged. So this is the typical example what we can see again when we give this to a physical picture. So they are just almost non-interacting in this milk. They come close together in this aioli. It's also a possibility that they just lump together completely, but this doesn't play a role today. So this is a phase diagram, so to speak, for this jamming transition. So when you increase the temperature, all things get faster, particles move faster, or droplets move faster, so they can eventually escape. So the jammed emulsion is behind this triangle, which is here in the front, and close here to the origin of this coordinate system. Between this origin and this triangle here, this is the jam phase. And also, if you increase the density, if you make the density of the droplets bigger and bigger and bigger, so it's 1 over density. So if this density becomes larger, the 1 over density becomes smaller. So you move in this direction. So high density is jammed, low density is non-jammed. And of course, what's very important in the mouth, because in the mouth you apply some shear stress, because you move your tongue against the palate, and this gives some shear stress to the emulsion. And when this shear stress has a critical shear rate, shear amplitude, then you can release it, as you will see later, and then becomes unjammed. So this is a nice phase diagram, which is developed for physics of emulsions, for physics of all sort of systems, but which applies here in our case for the culinary application as well, because this is exactly what we do in the mouth. Because if we have a cold emulsion, we increase the temperature. If we move it in the mouth with the tongue, we shear it, and the density we don't change. So this is perfect what we will see later on as well. And what what is the basic physics of this emulsions? Now this is physicists oil drops. They are squares because we are simple-minded persons, so we make life simple. Because a sphere is more complicated than a sphere, so because a cube. So we just assume that this cube has 10 millimeters. Then we come with work with some device like that, and we divide this into cubes with 1 millimeter. So the volume remains constant. What we see here when we calculate the surface of this is why I choose the cube. Then I don't have to worry about pi's and factors. So when we divide this into 10 small cubes, we increase the surface by about factor of 10, by about the number of particles. So this means that here when there is water around this oil cube, and when there's water around this oil cube, these oil cubes are exposed more of the interface, more of the surface to the water, which costs more energy. So the energy, forget about this formula, is just larger. And nature, physics doesn't like that, because in physics we know principles. The first principle is that the energy goes to a minimum, and when you stop moving your whisker, they just join together again to form a big droplet, and they go to the surface. This is what we know. So we need emulsifiers, and the classical emulsifier in the kitchen was for a long time egg yolk. So it's water, lecithin plus protein, and so on. So there is a phase compatibilizer and things like that. And this is just lecithin, which is just a molecule which has some sort of, which looks like a fat molecule. So these are two fatty acids. So this is hydrophobic, and there's a polar group. This is hydrophilic. This is much more cartoon here. Because here it's a sort of nitrogen, oxygen, they are polar, so this is water soluble. Here two fatty acids. In this model it looks like that, and for a physicist it looks just like that. And we know that from nature because it is in the membranes of all cells, of all biological cells, of plant cells, of the cells in the egg yolk. This is also one reason why we have it there. And also for human cells. So this is a universal molecule in nature, which it can use safely and which doesn't make problems. And this is also still known in the modern Spanish kitchen. This is this lecithin, which you use in almost every day. So this works, but the theory is too simple, because if we beat it now, if we just make the simple experiments that we put up some oil and some water, and we just put a little bit of egg yolk, it becomes a stable emulsion. So the oil distributes to the fatty acids, and the water distributes to this one, to this polar group, this polar head. And so this becomes a nice mouthfeel, because it becomes creamy because of this reasoning, because it's all jammed more or less by the cage effect, because we succeed to distribute the oil in small and many droplets. But this is too complicated, because the egg yolk is just a little bit more, and we don't know really what emulsifies here, because it's water plus lecithin. This is true, but it's also proteins, and if you look close to egg yolk, so what you see the plasma, which is basically some water. So you see here LDL particles, which contain the fat, which are again surrounded by special proteins. Then there are granules inside the waterish phase, which contain also lots of proteins, which has a function of the nutrition for the growing chicken inside the eggs when it's going to be breeded. So there's all sorts of things inside, and we, as a physicist's point of view, well, we know that it works. We can get nice emulsions with the egg yolk, but as a physicist, when we look with the physicist's eyes on it, we really cannot distinguish between the emulsifying properties of all these different components. So we would like to have a better understanding, and we would like to make the system simpler, to go away from the egg yolk, just to have a sort of clearer physics. Now, it's too complicated. I wrote here as a headline, just take egg white. egg white also forms perfect emulsions. This is even a picture from one of my cookbooks, but this is all in German, so I cannot recommend to read it to an international community. But of course, what you see here when you look this emulsion here of the egg white, so you see also droplets. You see droplets. This is not so much oil inside, so it's a step between. I've chosen this picture deliberately because you see here still remainers of the foam, which the egg yolk builds also. So excuse me, egg white builds also. If you beat it, you get foams, and you see here the rest of the foams. And when you increase the oil, you just fill oil inside, and the foam gets destroyed, and the air inside the foam bubbles becomes replaced more or less by the oil droplets. So oil, foams, and emulsions are more or less the same, similar physical systems, because air is also hydrophobic, oil is hydrophobic, and so it's more or less similar physics. So we can really simplify the system by just using the white of the egg, because twice is simpler. No, this is a terrible transparency, but I would really like to show you at least the physical principles. I will explain you that. Don't worry. Don't get frightened. So this is a simple picture of egg white. So this is water, which is this gray spot here, and there are proteins inside. Now there are more proteins inside, but I've chosen just one, which is the ovalbumin. The ovalbumin, when you look in the protein data banks, looks like that molecule. So it's nicely folded. It has helices. It has beta sheets. All these things we know from biology, which gives the protein structure and function, and makes it dissolvable in water, because it has to be dissolved in water. But when we look at the structure, when we look at when we put our feet here on this molecule, and we walk along this molecule, we walk along the path, and we look at each amino acid which is inside the proteins, we get here letters. Each of these letters, what you see here, they are just correspond to amino acid, which is at the moment not important which one it is. But there are different colors here. And the different colors is green, red, and blue. And what it says here is the blue colors. These are amino acids which don't dissolve in water. The red amino acids, they dissolve in water because they are negatively charged. It is a glutamic acid, the aspartic acid. The green amino acids, they are positively charged, like leucine and histidine and so on, and they dissolve also in water. Now, if we know something, now if you look at this whole structure, so what we see here is we see a direct change of water dissolvable and non-water dissolvable blocks of this protein. And so we have the idea that this is a perfect emulsifier, because the hydrophilic amino acids, they will go to the water phase, and the hydrophobic amino acids, they will stick to the oil phase. And so what happens is, just as we see here in this cartoon, so we just put the egg white, we just beat it, we have added no oil, can add oil later. What happens is, by the mechanical work, this protein denatures, defolds, and turns into a snake, like this monster of Loch Ness. And what you see here parts which go to the air phase, and the other ones here, which are invisible, remain in the water. And this is exactly what some of these proteins do, and this is why some of these proteins are perfect emulsifiers. Now, we did a simulation of something like that. So what you see here, we just have constructed a simple protein, which is not a real protein, but just a physicist protein. And this is the oil phase, this is the water phase, and the red one goes to the oils. I change colors here. This is didactically not very nice, but if you wait for some time, if you add some energy, then the protein distributes just by itself on the surface, on the interface between oil and water. So it's localized at the interface, and when it's localized, it means that it remains there, and then if it remains there, it is an emulsifier because you can get it there by mechanical energy. You defold it, you get it by mechanical energy in the interface by beating the emulsion, and then it remains there because it feels happy because the energy is at a minimum. So it remains there for a long time, and this means the emulsion is stable. So now we have different emulsifiers here in the kitchen. Well, this is phospholipids, this is lecithin. We have also monoglycerides, sugar esters, like you know from texturas and things like that. We have also particles, and we have proteins, which I just have discussed. Now, particles is also interesting. I will come to this later. Now we have two types of emulsions. This is just for completeness. Oil in water emulsion, because here the oil droplets are dissolved in water, so the water is in continuous phase. Continuous phase means that you just can walk or swim through the continuous phase, because you can reach most of the points here by swimming through around the oil droplets. The oil droplets are discontinuous phase, because if you put yourself in oil droplet and you begin to swim and you just reach the border here and you cannot escape from it. So this is continuous and discontinuous phase. The inverse emulsions, which physicists call, or physical chemists call inverse emulsions, is the water in oil emulsions, like butter or margarine, for example, because there's the water droplets inside a fat phase. So they are completely different emulsion, and this is why we need also sort of different kind of emulsifiers. This is just the picture which I just we know different emulsifiers for producing these emulsions. This is just an example, because this is monoglyceride. I think it's glyce or glyth by texturas, and this is just you just steal one or two fatty acids from a fat molecule, so you remain with that. So this is weakly water soluble. This is highly fat soluble, and what you get, you can easily produce a honey olive oil emulsion, which is a sort of inverse emulsion, because the olive oil is outside, because this is really weakly water soluble. So they stick the heads together, enclose the honey here inside small droplets in an olive oil emulsion. And what you can do here is you can just put that on a plate, and you can put it on can use it as an inverse emulsion on your plates, for example, with chicken or with, I don't know, what else. So there are some physical principles which you can carry in the kitchen and carry from the lab in the kitchen, and vice versa. And this is quite nice. And this is also an example like that, just for entertainment. We have also particles which are emulsifiers, because the particles, they just sit sometimes on the oil water interface, and with a sort of angle here, and the energy of the surface energies you can calculate with this angle. This is too much theory, but you can try sometime. You can try some starch, some small starch particles, and you can just mix it with oil and water, and then you will find a sort of emulsion, which is a Pickering emulsion, because the person who has invented this kind of emulsions, his name was Pickering. It's a name because the starch particles, they will just collect themselves around the oil droplets. And the nice thing is, you say, why do you use starch? Because we can heat it. We can heat the emulsion in the oven. Then the starch gelatinizes, forms sort of crispy hard layer around these droplets, and then you get emulsions which are just which you can cut like pommes frites or like French fries in sticks. These are full of olive oil, and it even gives you a crispy mouth feeling, because the starch does not care about the oil. The water is taken up by the gelatinization, and it's crispy. And if you put some only olive oil, salt, and water, then it's already a sensation. If you put more taste and more things, you can become creative with some sort of nice giveaways for the guests, or give on plates as a sort of funny surprise. Now, I would like to extend these ideas to some kind of new things we studied. Here, I would like to go a little bit more deeper. We made recently a study in a master thesis with milk and oil emulsions, because I was fascinated by this idea to get stable and good emulsions by just mixing milk and oil, which I did for a long time in the kitchen. And so I just didn't understand. I could guess the physics, but we didn't understand it. So a student was interested, and we just made a master thesis out of it. So now what you do is you do just a classical thing, yeah, just whisk it all the time, and then what you see here in the lower picture, you add some oil and you add some more oil, and you get stable emulsions, which from the photograph what you see here, more or less from this top picture. Now in the laboratory we mix definitely with some defined frequencies to get it reproducible. These are this ultra thorax, which most of you have in the kitchen as well. Every chef has in the meantime such a nice device for making stable vinaigrettes and things like that. So this is quite nice, and you get these emulsions, and we needed it just to have reproducible because we want to do research on it. Now, what is in milk? Now you look into books or you look in the internet. Now you see most of nutritional values. So you see fats and you see non-fat solids. You see also water. You see sugars and things like that. You see lactose and all these things. So now you look into more of the physicist's eyes. And what you see is there are fat droplets inside, there are proteins inside, and there are casi in micelles inside. And so now the question is what emulsifies? What of all these things emulsify? And this is not so easy to answer. So we have to ask for length scales. Which are the relevant length scales in this of these things? Of course, there is water minerals. This is what's inside, what is the whey, part of the whey, and these are just small scales which we don't have to care. Lactose, vitamins, forget it, too small. But here we come into ranges 10 nanometers to 100 nanometers, lactalbumin, lactoglobulin, serum albumin enzymes, and things like on casein micelles. These casein micelles. This here is the alpha lactoglobin. This is the alpha lactoglobin. These here are the beta lactalbumin. Excuse me, beta lactoglobulin. It appears always in pairs, and these are the casein. These are the casein micelles. So now we can guess that, given the knowledge from the egg that we had already by beating some of these type of proteins, we can also expect that some of these proteins just open up by beating and eventually by heating. So because we know from milk cooking that these casein micelles, they are stable until 124 degrees. So they will not be able to contribute significantly to the emulsification, the emulsifying process. So we expect that one of these or both of these proteins, these whey proteins, will contribute to this process. It's just for information, the fat droplets. So we know milk fat is basically butter. So butter is at room temperature solid. So the cold milk. So you have droplets which are solid. So they are crystalline layer outside, liquid fat inside, because there's a broad fatty acid distribution. There is this lactalbumin, lactoglobulin here a little bigger. The casein micelles, which are here beta and alpha casein in this highly fattish, hydrophobic submicelles. They are linked with calcium bridges, and so at the moment they are very stable, so that they don't contribute to the emulsification process. It will be something like that. You see this both, they are not bond here together. It's just an interaction. Yeah, beta sheets, so it's not a very stable pair which here appears. You can separate these two immediately by just increasing a little bit the energy, and then they are separated, and you can have a hope also that you can denatured that by BT. So these are the hot emulsifying candidates. Indeed, if we do this experiment in the lab and you start to take on same take an amount of milk, a certain weight percent of milk, and you add 70%, 71, 72, 73, 74% of oil. So it's quite a lot of oil on top of that. So you see in the microscopy, you see here stable emulsions where you see droplets. They are already squeezed. They're already really squeezed. So they're already really good, really nicely caged. And when you increase the fat droplets, and then you get the droplets even smaller, even more. So there is really a stable emulsion which has really a good property, almost as or even more solid as which you get from egg yolk. So milk is good emulsifier which you can use in the kitchen. You can just look at the particle distribution. It's just a sort of just checking all things as we do in science. We like to understand these things in detail. So we just look at the things. So we have a machine where we can measure this particle sizes, the oil droplet size. This is a little bit tricky, but it's possible. So you have to dilute again. You have to put it in this machine, and the machine puts some light on it, and the light becomes deviated, scattered by these oil droplets, and from the scattering angle, you can measure. You can get the sizes. Crude method, but the effective method. And what you see here, if you increase the oil concentration, you get smaller droplets. So if you, this reddish curve here has much smaller droplets because the maximum here is at smaller droplets than the blue curve here, which has higher droplets. So the size of the droplets it's decrease with the increasing oil concentration. Now, what has this to do with mouthfeel? Now, of course, we have to study that in more detail. What happens in this? With what do we mean by mouthfeel? So, as mentioned before, if you put this this emulsion in your mouth, you have the palate, you have your tongue, you squeeze on it, you shear on it, and when you look inside this emulsion, you see, of course, all these droplets. And of course, we cannot measure forces in the mouth. This is just not possible. So we use a simple device, a simple machine, which is called rheometer. So there's a plate, which is the upper plate. There's a lower plate, which is the tongue. And we put the sample inside, as the emulsion inside. Then we rotate this in the oscillatory. We can even also press on it with a loading force. And we can see how this thing reacts. And from that, we can measure the force. We can measure even the response to the shear. And so we can quantify what happens in the mouth. This has, of course, several disadvantages because at the moment we use here classical rheometer plates, which are metal. And our tongue is of course, biological material, our palatine as well, so we should use other plates, but for a moment it's okay. There is no saliva, there is nothing which adds water to the emulsion during oral processing. All these complications I'm not going to discuss here. I just would like to understand in the moment the properties of the emulsion. So you see here, after some shear, it's broken. So it's like something like you do in the mouth. This is the device. This is just the device how it looks like. So you can change temperature here in a definite way, and you can do a lot of nice things with this machine. So what do you see always? Now you see always two curves because by these oscillations here, so you can measure also the elasticity, but also if there are fluid parts, you can also get the viscous modulus. So the modulus is just a measuring a quantity which measures the resistance to the shear, to deformation. So it's a normalized quantity proportional to the force. So a high modulus means high bite force, high force in the mouth. But if it's liquid, you know, a liquid, a juice, a honey has some resistance, but compared to water, Oil has less resistance compared to honey and things like that. So you have also liquid parts inside the tongue, and this is always lower than the elastic modulus. But if something happens with the material in the mouth and you shear it more, you just shear it more strongly, you have more amplitudes, you shear it wider, you just almost and you rupture it, then it becomes possible that suddenly the liquid force becomes larger than the solid. And then the structure is broken. And before it's broken, you see here a typical hump, which is the caging effect. So we can expect to you when we use this model, this model experiments, just to learn something about all these things. These are the measurements for the. It's just not so interesting. It's just confirms what I just had done before. I said before. So the different emulsions. So they are quite nicely, quite stable because it to 10% deformation, which you reach easily by your tongue and palate, they are stable. But suddenly, if you just chew and more intensively, move it more intensively, then the structure becomes together and it becomes more liquid, and it becomes from a sort of kind of creamy solid to some sort of liquid type. So we can also look at it with an optical system. So this is what we can look at during the shearing with this you just look with a microscope through this rheometer, and what you see here, it's quite interesting. At the beginning, nothing much happens. You see droplets moving. Now the shear becomes large. The droplets are sheared, and suddenly they just break together, and now this is shortly before you swallow it. Yeah, so you see here directly how these objects move with this definite shear rate. So you can really follow the particles here quite nicely and see what happens during the shear. This is quite surprising because you can follow things by looking at it via a microscope and taking pictures and taking these things. This is the same once more, because we try to see how much is the cage effect and things like that, measure it. So we took different time lapse, but this is the same picture. You don't at the moment, you don't learn much more. So what we can get from that is really a complete understanding of this curve. So at each, you can follow at each curve, you can address to some pictures, and you can try to understand what's happening in the mouth, and you can see which particles may get first instable, which particles have the highest mobility and things like that. And the response from this measurement is, what can I do to improve emulsions? Now, what can I suggest? Is it better to have a distribution like here, where we have large droplets and small droplets, or shall we just aim for equally sized droplets and things like that? And this is something which you can really study in detail, depending on emulsifiers, depending on culinary systems, and to see what happens. This is quite interesting to combine the visibility and the mechanical response in the mouth. Of course, the next step will be to add saliva and to add sort of different plates to this rheometer, so that we shear it not on glass plates. Well, when we want to do microscopy, we have to use the glass plates, but for the other measurements, eventually to use rubber plates or something like that, which are more soft like the tongue. So now you get something, what I mentioned before, a complete sort of phase diagram. We can fill this phase diagram, which I mentioned before, which I introduced before, with some nice pictures and physics. So here in this outside this triangle, the droplets are quite separated. So it's liquid more or less. At the border, it's just confined. Here it's more confined, and the more energy you put in, the more it becomes confined. The more the density increases, 1 over density here again, it becomes confined. And this is what you do in the kitchen. This is what you do in the kitchen, the preparation. by choosing emulsifying system, by choosing your flavor system, by choosing your emulsifiers, by choosing the kind of oil which you would like to use for this emulsification, the flavors, everything. And this is where you see the guests, because they have to sit on the table and do the oral processing, and so they need to be pleased by this emulsion. So they need to be sure, or you need to be sure that you prepare it nicely so that the guests are happy. It's a kind of childish remark, excuse me, because this is, of course, nothing to discuss about. So for science, of course, we used also reconstructed milk for deeper insight. So we looked at this protein separately. So we made two emulsions with whey protein and the other one only with casein. So this is just, you see, you get it also some kind of emulsions, but the stability is less, and you have really to add a lot more than the milk brings. So this you can do, but it's of course, you have to think about that if you use, for example, pure whey proteins or pure casein, sodium casein, which you can buy in shops and things like that, and to make these emulsions, like in industries and food industries using these things to emulsify creams which are processed industrially and go to the supermarket and things like that. But why we did that? Because it's a quite interesting experiment, because you can heat the milk emulsions. You can heat them in your oven to get it sort of to gel it. They gel. They form gels. So you have been interested what makes the gel. So this is the milk. The blue one is the pure milk, the classical milk. So it gels here. You see it. You start with a modulus, which is liquid, and you get an increase of about one degree of from 10 to the 3, 10 to the 4 roughly. When you do the same with casein, it just increases, but it drops again. So not really very big effect. If you do this with the whey proteins, they really make a big jump to form a good, really gel which is almost cuttable. You go here from very liquid to very solid. And this is a good news, because this lactoglobulin, it has a different property, because it has an amino acid which is called C, which is called cysteine, and it has a lot of cysteine inside, and this cysteine has nice properties, because the cysteine has here this SH, which is a sulfur and a hydrogen group. And you know, sometimes if you drive car, you drive on vulcanized rubber, and the vulcanization in rubber industry is sulfur. So the idea is sulfur is also a good food vulcanizate. Vulcanizates also foods, and indeed it does, because if you heat it up to about 65 to 72%, this H goes off, builds water, and these bonds become chemically free. Clack, they can form a bond. And this is what happens. So this is responsible for gel formation, because this is one lactoglobulin, this is the other one. It's also likely that it gets inside closed, but also outside, and this makes a good gel, lactoglobulin's gel. And this is quite nice, because you can put, I just put the beaker, this is for my home kitchen, you put just the beaker with the milk gel, with the milk emulsion in the oven, heat it up, and then it's quite nice gel. And if you eat that, it has even better mouth feeling compared to the emulsion, because there's a little bit of elastic response, and you just by further food processing, you just cut the network, and then you have the emulsion left, and then you have one sensation, one textural sensation more. And this is also exciting when you flavor this correctly and all these things. So these milk emulsions give you a lot of kind of possibilities in the kitchen, just for physics reasons. This is quite satisfactory for a physicist. Now, what about, we speak a lot, at least in Germany, we speak a lot about plant milks. So I just have chosen for a moment the soy milk because I use this in, well, we should not call it milk anymore according to European Union rules, but yeah, I call it within us soy milk. So it has nice properties. It foams. You can even make olive oil foam with just beat a little bit of soy milk. You add some olive oil. You just beat it with a sort of mixer, and you get nice stable olive oil, nice sensational with fish dishes and things like that. Nice bubblish mouthfeel, and you can also get it in a espuma with some chocolate and things like that. So the fat content increases here, and you really have nice emulsifying and foaming properties. This is something which we made here in the lab. It's a chocolate cream with soy milk. So what is with the soy proteins? Now, given the knowledge which we have already, we have storage proteins in soy milk, which is some kind of albumin. It has also some properties, as we know before. Okay, this is good news. There are even longer storage proteins, glycine. Again, a terrible transparency. I apologize. But again, what you see here, just as a sort of repetition, if you look at this primary structure, there are two of these things which is inside this soy seed, the leguminose. There are even 3 and 4. But if you look at that, you see again this blocky structure. Yeah? You see blocks which do not dissolve in water. This bluish one, you see reddish one which dissolve in water, a bluish one which do not dissolve in water, right in a sort of blockish way. And we can expect again that soy protein is again extremely good emulsifier. So what keeps us to do to make this chocolate creams? Now let's go and let's just do it. Hot soy milk, add chocolate, emulsify, cool down, but then the chocolate becomes solid. It's a big difficulty. And this is the thing which I have shown you before, because we know that chocolate becomes solid at room temperature, solid, 22 degrees, it's solid. Now what happens? But this is some complication because the chocolate or the cocoa butter, which is fat in the chocolate, has to emulsify in the droplets. They are confined. There's emulsifier around it, so it cannot cool down and cannot crystallize as in bulk, as in the bar of chocolate. So, but how does cocoa butter crystallize in emulsion? What are these fatty acids? I think we know that, again, these triacylglycerols, they have different saturation degree and things like that. So they can crystallize the simplest fat. This is just a tristearine. There are no saturation. This is unsaturated, just saturated fatty acids. In the liquids, they are disordered. Now, if you cool fastly, so they go into certain phases, these molecules, they just stand oppositely each other like two forks. When it's metastable, so they jump into they gradually go into a beta prime phase, which tilt a little bit, and then beta phase, which tilted and again, and you see they become smaller a little bit and can grow easily, and all these things which chocolate producers fight every day with such kind of problems. So in the cocoa butter, we have mainly the main component is a fatty acid, which has its oleic acid, which well known from olive oil, which has here one bending, one cis bond, which is unsaturated, and palmitic acid, which is a little bit shorter, and stearic acid, which is also well known from olive oil. So it has a little bit shorter. And these two different defects, so to speak, they make problems in the crystallization, which makes different sort of polymorphs, different types of crystalline structure, which you again feel in the mouth. This is a huge classical chart from the chocolate producers, because there are these different polymorphs, these different sort of crystalline structures. They are called polymorphs. They have different melting temperatures, and it starts here with the very low one, 70 0.3 centigrade, which is there would be even liquid at classical room temperature. And this alpha phase, which was this one more or less, this alpha phase 23, and beta phase is 20, 25, 27, 23, 26, 36, and this is summarized again, but for chocolate, this is stable, but this is not desired, and you see this when you forget about it, your chocolate for a year or so. It becomes difficult to process orally. It will not melt properly. It will it will not melt anymore because the melting temperature is too close to your body temperature in the mouth, to the tongue temperature. It is not stable. It is too stable, and you have to bite it into small pieces because your heat content of your heat energy of your tongue can melt the small crystals. So desired is this one, and so this is why chocolate producers do a lot of efforts to get this crystal phase. Now, when you look at it in bulk, the crystallization, we just did it in a different purpose in a different study in a paper. So we have to wait under the microscope. This is liquid cocoa butter. And you see here some nuclei starting, and it gets boring, but it gives us a break in the talk just to watch a video quietly. So it grows and grows and grows, and becomes really boring. This is even time lapse. I have to say this is overnight. So the video recording on the microscope overnight, and now you see shapes coming up. Needle-like things come up, it starts to become irregular. So this grows nicely here, irregular shape. This grows. Now they merge eventually. Will they merge? I don't know. The other ones here, it also has needles. They will not merge. They will just make room between each other. Here as well. They will keep separated. Now you see still they are separated here. Here, there's a lot of things. It's like a growing star sky in the night. And what you see here is you form these crystals and crystals and crystals, and so this is like bulk chocolate crystallized. Now let's just take this idea, and we heat now soy milk. We add molten cocoa butter. We emulsify and we see what happens. And this is already a microscopy picture of this liquid emulsion. And you see again droplets. We have to look at it more closely. So we do not, in this study, we did not use, it was a recent thesis by Isabel, a student in our group. She did thesis on that. But we did not use pure soy milk for the research, but soy proteins, only the proteins, just to have not all these cellular materials and disturbing things inside. Now we did the same. We prepared with 4 weight % soy protein dispersion, and we added 55%, 60, 70, and 75% cocoa butter, and we see that we can also control the droplet size quite well. We get stable emulsions for everything, but as long as they are liquid. Now what happens when they become solid, when the chocolate crystallizes? But here I will just not discuss that. It's just it's the varying protein content. You can control that. It's not so important for us. Now what happens when they crystallize? Now let's watch this video again. This is now what we see at the beginning. Is this liquid oil droplets, different sizes. The protein is outside, the water is outside in the continuous phase, in this darker phase. Now let's watch what happens. I hope this works. It works. Now it crystallizes. There's still some motion. It starts to crystallize. The 45 degrees is only the polarization angle. Don't be distracted by that. So it's has nothing to do with the sample. So it crystallizes inside the droplet. It crystallizes. You see this kind of needle type structure. It becomes brighter because of the polarization microscopy. And now they try to leave all these droplets. And now what happens is it starts to break here. Now you see here it breaks. The emulsion breaks because of crystallization. It breaks here as well. It breaks here. It breaks here, so it's very exciting. What you see is like a Western movie, as exciting as a Western movie. So this is something which is of course which disturbs the stability of this emulsion when it breaks due to crystallization. This is really not so much desired, and now we can do the same in the rheometer. So we just measure the modulus because this is a liquid emulsion. Now it crystallizes, so it becomes solid parts inside. So the modulus increases; it becomes more solid in the mouth as well. And now you have you can address to each of these steps here, the crystallization steps. Here it's liquid. When it's up to here, it's liquid. When it becomes here, it starts the crystallization. It becomes solid, and we see that here in this crystalline phases. Crystalline microscopic picture with these needles and with the different reflections in the polarized microscopy. You see here the crystallization. Now this is going on. First of all, there's liquid, and then they eventually merge, and then they form. As in bulk chocolate, they try to form these particle shells. They try to form to come together. Because they are hydrophobic, because this is fat. They have just disrupted the emulsifying layer of proteins by crystallization. They want to, and then they break the emulsion. They form, so to speak, an inverse emulsion. And this you feel also in the mouth. So it's now difficult to see. And also, if you reheat these emulsions, you will not get it stable anymore, because you will really provoke a phase separation if you reheat this crystalline. If you reheat this crystalline emulsion to 40 degrees, then they will just break completely, and they will get a macroscopic phase separation. That the cocoa butter will be on top, and the water and the proteins will be below. So what is the message? That message is you have two ways. Either you want to have perfect chocolate crystals inside the broken emulsion. You have to cool it down slowly, and you reach this one, and you can just hope you have enough chocolate inside that the inverse emulsion will give you the flavor and the liquid phase. Or you prefer a more creamy emulsion, so you just cool the emulsion quite quickly, so that you have imperfect crystals, but smaller crystals, because they don't have the time to run around and look for his partners, because the cooling is so fast that they get stuck somewhere. And so they will remain in their places, and they will have smaller crystals, but imperfect. They will melt more quickly, and they will melt more quickly in the mouth, but the emulsion will be more creamy. So you see here, from a physics point of view, we can even from all these abstract, so to speak, experiments, you can even make a sort of take-home messages for your own kitchen. Now, I thank you very much that I was invited to this lecture, and you see culinary science. It's always curiosity and pleasure. We go close to Christmas, so this is this sign, and I'm happy to answer any questions you have. Thank you very much indeed.
Thank you so much, Thomas. It has been great. It has been so interesting, all your talk. We have some questions here. I'm going to read them for you. You said the first question says something like, how stable is an egg white emulsion compared to an egg yolk emulsion?
It has about the same stability. Yeah, it has about the same stability. And also because the egg white, we know from the egg white as well, it forms gels. If you don't heat it too much, because then it will collapse again, but also you can heat the egg emulsion to make it little bit solid and elastic. So it has about the same stability.
Okay, because I mean, when you were talking about the milk emulsions, are you talking about the so-called lactonase? Because I mean, in cooking terms, they I mean they differ between the mayonnaise and the lactonase when that emulsion is made by milk proteins.
Yeah,
Okay.
no, we used milk, and then in the other experiment we used whey protein isolate and casein isolate on sodium caseinate and things like that. But basically, we used natural milk. Most of the thesis was done with milk, but we defatted it. We defatted it here in the lab. We used always the same milk from a producer, and we defatted it to have almost from the same sort of type of milk.
Okay, excellent. There is another question. What would be the best way of making a vegan stable mayonnaise? Is it soy protein enough?
Um, Not really. I would prefer a mixture between soy proteins and pea proteins. The soy protein gives, because it's long, it gives you a good elasticity, but for the small droplets, which you also create in a normal kitchen emulsifier, it's wise to have a sort of mixture also between soy proteins and pea proteins, because then you get a good synergetic emulsion, because both of them, because the pea protein is a little bit shorter from the length, and it can overtake another length scale, and so it's also because, but soy milk proteins, you can, what also is, when you don't want to use a sort of second protein, I would also add some hydrocolloids, for example, um, depending xanthan or let's say carrageenan or something like that, just to reduce the viscosity so that the emulsion remains more stable. Um, but this depends on the flavors, on the culinary properties which you want to achieve.
Okay, okay, thank you. Thank you. Another question. It's focus on for the functionality of lactoglobulin, beta lactoglobulin, and alpha lactoalbumin. Um, the question is, why does lactoglobulin and lactoalbumin emulsifies when it's hot? Could you do it when it is cold?
Yeah, we know we did all things have been emulsified with room temperature. Right? The emulsions have been carried out in room temperature. They are quite stable. Uh, the Katja, who made this thesis, she did also, because she's an engineer, and she also made for herself a stability experiment, and it was stable from the emulsion stability, not from microorganism stability, but it was stable for more than 8 days
All right.
in the fridge. Yeah, so it was without heating. Yeah, but of course it's dangerous because the microorganisms which might grow on that. But it's, from a physics point of view, it's quite stable, and you can do it without heating. When you add heating, you just get an additional stability by cross-linking the lactoglobulins because of this desulfide bridges.
Great, excellent, thank you. Some question about the, I mean, regarding the chocolate example you gave. The question is, the inversion of the emulsion during the crystallization of chocolate is similar to the inversion from heavy cream to butter.
Yes and no, because yes, because it's a similar physical process. No, because the origin of the process is just not the mismatch between emulsifier and fat, but the mismatch between emulsifier and de-shaping by crystallization. Because when the crystals grow, the the droplet doesn't stay around anymore because the force by the crystallization is much larger. The energy gain by the crystallization is much larger than the binding energy of the emulsifier of the emulsifying proteins around the droplets, so that this gets disrupted because they just get kicked out of the crystal. Yeah, because crystal doesn't like foreign bodies inside. It's causing defects, and if there is a tail of a protein inside, it gets kicked out by the crystal formation, and so it disrupts, and then there's a different process. But basically, from the basic physics, it's similar to the emulsion version.
Great, thank you. There is another question regarding the meringues. Just to make meringues, could you use animal blood as an egg white substitute?
Yes, yes, that's a good idea. I'm a fan of that. No, you can, indeed, you can use animal blood as a egg white replacer for forming meringues and things like for good dishes. It gives a great taste, and you can add all these flavors from a good dish which uses kidneys and liver and things like that. It's possible, yes, because it's the blood is underestimated in kitchen anyway, because it has it has a high nutritional value. It's from a nutritional value, it's really a good substance, and it has, of course, it has all these water soluble proteins which also get denatured by beating. It has peptides, it has quite a lot of free amino acids, it has fatty acids inside, it has also this LDL and HDL particles which help a little bit the stabilization by viscosity. So you're welcome to do this meringues and this foamy things with blood.
Great.
Great. Thank you so much. This is a good question. I'm a fan of such things.
Excellent. And there is another question. Which would be the best stable or the most stable vegetable source on emulsifiers for you?
Yeah, pea proteins, soy proteins. There is maize proteins or corn proteins, not so much. It's basically pea and soy is good. If you get lentil proteins as well, mostly there is. I don't know. There is a in here in this country there is a great effort on. I don't know if it's English. Lupulus.
Yeah, lupin. Yeah.
It's also well known in Mediterranean as a snack with the pastis and with the as an aperitif. And extraction from lupins in protein fractions from lupins are also good candidates for this.
Okay, thank you. Yeah, there are quite a lot of new kind of products where you can get some nice proteins, some emulsifiers. Yeah. Okay, there is another question. What do you think about the reduction of emulsifiers in industry, in the food industry?
Yeah, this is a good idea. Physics can help that because I have plenty of discussions on this issue, because you see normally what's done in food industry is they don't look at the physics, they look at the process, and they look at macroscopic scales, and then when something works, it works, and then it doesn't work because there's a component different, then you add something. But in contrary, you don't remove something. Basically, you don't remove something, and so it can be done with a more physical point of view. On the other hand, it costs money, and the industry avoids that. So, but with a little bit more with the physics view, it can be reduced, because some of the food ingredients which have to be inside anyway, they have already emulsifying properties, and sometimes the process needs just a little bit 1 or 2 centigrade different temperature, then it works again, and things like that. So it's a good idea to think about this, because the consumer and the people who the buyers, they don't like when they read lots of lists with emulsifiers. Also, they are not dangerous.
Yeah.
Not
Okay.
dangerous.
Yeah, yeah. Okay, thank you. I really like the example you gave about pickering emulsions using starch, tapioca starch, if I remember. What is the size of the starch when it is absorbed in the interface?
And it's about my 10 to yeah, 100 micrometers.
Okay, and
It's broad because it was a commercial tapioca starch which I used.
okay,
So it's a broad distribution. It's not.
right.
This can be definitely optimized. The smaller the particles, the better. But starch grains, or the starch grains itself, they are the limiting, and tapioca starch is known as to have a small grains, starch grains. But
Okay.
you can use also other starches.
All right, and how do you introduce the starch? How do you dissolve it? Yes.
No, what I used in this experiment, I did it even at home. It was tapioca starch from home. I just took it later on to the lab to look at the microscope with it, and I used just a little bit of salt, a little bit of soy sauce, a little bit of water. Don't ask me; I don't remember the precise recipe.
Right.
Then I added starch grains. I just mixed that with a mixer with a, I don't know what it is in English. So this is
Yeah.
a kitchen ultrathorax.
Okay. Kind of. Yeah. Yes. Yeah, but I mean, it's a kind of a
Yeah, a
mixture
fast.
with. Yeah. Okay. Yeah.
I can make it fast.
Kitten
I,
eight, maybe a kitten eight, maybe. That's a
no,
kind of equipment.
you use it by hand, and it has
Okay.
a long rod,
All right.
so it's like
Yes.
I don't know how it's going.
Yeah. Well, I kind of. Yeah. 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 I know the name in Spanish too, but not in English.
I can send you later on a picture of it.
Okay.
and
Right.
then and then I just put this on the table, and then I put energy, and then at the same time I added the olive oil,
Yep.
yeah?
Yep.
And then I added with a definite, not as much as possible, but just in a small amount always.
Yep.
And then I mixed it until I got a stable emulsion. And of course, this is not a good culinary emulsion, because these grains are,
Yep.
yeah, because there's no point with it. But the interesting point was just to put it in the oven and just to see whether it's stable, whether it resists heat, and to gelatinize the starch, that it forms a sort of crispy layer around it, because it takes up all the water by the gelatinization, because the amylopectin melts and things like that, and then it got really crispy. And what you have seen on these transparencies, I took it out of the beaker, and I just could cut it into this
Yeah.
French fries form, and it was nice, crispy. And so I did this several times with other flavors and flavored oil, like orange inside, and of course a little bit oilish, but it's healthy. Olive oil is healthy.
Yeah. Okay. Thank you. Um, more kind of general questions. Because I mean, it has been some debate between the use of artificial ingredients when Ferradria, for example, started years ago to use these kind of thickeners or gels, artificial ingredients, into the kitchen. Um, some people started to say that that's not natural, and you cannot use that. And what do you think about that?
No, but most of the things, which came to the kitchen are indeed natural materials. Well, carrageenan, pectin, things like that, lecithe, I don't know what else. Now we discuss now about future food. It will be algae from the seaweed and things like that, but this is full of carrageenan. We eat that. Other cultures eat that as well. Agar rose or agar was eaten in the. I have known agar. I did my postdoc in England, and I got a friend within Indian community, which taught me the Indian kitchen, and they used agar rose, agar since a long time because it's the only plant gelling agent in India, which is used by Hindus, and it is the only gelling agent which gels at tropical temperatures. There are, of course, there are things like the sugar esters. I think it's called sucro in texturas. I'm not sure about that. Which are artificial, but food industry is using them anyway. If you use convenience food, if you eat convenience food, there is, of course, it's not. I don't think it's dangerous. There is no hint, no literature that it says it's dangerous. But if you want to avoid it, it's easy to avoid it. It's really easy to avoid it. It's just it was invented by food industry just to get this hydrophobic balance and things like that. And I don't know what was not artificial. What was artificial? I don't know what was in these texturas on this all these or sosa products, and I don't know which was not artificial.
Okay. Okay. All right.
I use it also in my kitchen at home to make fancy things, and I'm coming back to this. I was really delighted by this question about the blood, because I use the internals of bones. What is it? What is in English? What's inside the bones? This
Tuétano is in Spanish. I don't know in English.
Don't know in English.
But the inside, really interesting stuff. Yeah.
Yeah, it has good flavors, and I for making purees with it, I use this textura stuff, or this sosa stuff. It gives you a nice flavor because it tastes like a beef soup, and it's genius with vegetables. But I'm hungry now.
Great, absolutely. Another question: how is your kind of relation with the chefs or restaurants, or in your daily kind of work? Are you working more focused on food industry, or are they a kind of normal general research projects, or are you working with chefs every day, or could you tell us a little bit of that?
Yeah, I know. I'm well, since COVID, since the Corona crisis, working with chefs is difficult because it's closed everything. I work still with one chef close to Frankfurt. He is not a star chef, but a normal chef. Let's say he is a quite interesting person. He has an Italian father and a Spanish mother.
All right.
Was born in Frankfurt and has now a restaurant in Frankfurt, which he makes really high level daily cuisine. And we just discuss a lot, and we have just written a book about pasta, and I have done the science, and he has done the practical things and things like that. So this is a quite nice collaboration because we come to questions all sorts of. I have worked with chefs before COVID crisis, with three-star chefs in close to Cologne, where I did one day in the month, always the first Friday in the month. I spent the whole day with him to discuss and to study, and I took problems home Some problems went into the laboratory just for checking and things like that with our students. It's big fun for them. As a Max Planck scientist, I do more or less fundamental research. This means when I work with industry projects, there must be a fundamental component. I never do research where food industry pays me directly, and I measure 1,000 samples, and then they give them the measurements, and they can't publish this. We are not allowed to do that as a Max Planck Society. But I work with food industry. Like we have done some quite nice work with several companies, like who produce Xanthan in Germany, who produce Challen in Germany, who produce this this sugar alcohol erythritol, which is now a candidate for sugar reduction. We have a project with a PhD student on that, which is paid by the German government because of the restrictions. So I'm between applied science, fundamental science, chef science, so to speak, more or less equally distributed.
Okay.
It goes vice versa, and chefs call me, and when they have a problem, so they have my phone number, and they call me when they have questions and things like that. So it's quite open to that.
Do you think that in a way, this interaction between science and gastronomy could help to the new product design for the food industry, or could it have any effect into society from a nutritional point of view? What do you think about that?
I think this will become, well, I think this is already a sort of minor point, but it will become more important because with all these, when I look at this vegan products, which is more plant products, which are featured as we save the world and things like that, and sustainability and things like that. And I try some of these things from time to time, which is now in the markets, in the supermarket, and in the organic markets. And it's a need to try to put more effort inside, because as I mentioned before, because these people, they don't look inside the molecules. They try to make the macroscopic appearance more or less similar to a sausage or to a piece of meat, which you can put in the grill or in the oven. But what happens on the molecular basis is completely different, and you feel it in the mouth, because the texture is made by structure and the structure is made by molecules. And if you look at many products, like for example this sausages, this vegan sausage or vegan or vegetarian sausages, there are big problems to bring the oil, which makes the flavor release and the long-lasting taste and things like that, bring to the right place already during the process. Because when you look at a sausage producing like a Frankfurt sausage or something like that, the process is completely different compared to this what you have with the structured things and this mixing of these plant proteins, because of the proteins, because of the different sequences, because of the physics, because of the biophysics. And I think there is more need in future to do that. And I think that scientists like in your center, chefs like in your center, and people from industry should meet and should sit together and should discuss the basic problems and to sort out the relevant problems, and to sort out the base of the processes, the processing procedures, to get a satisfactory product for the final sensory test and things like that. There are many things that are missing there, because if you bite on some of these things, it's like a piece of rubber and things like that. The flavor release is different. I was recently trying a vegan chorizo, which is my favorite from the south of France. And it was really awful, I have to say. Knowing many different chorizo, had nothing to do with that. And I thought, okay, this is No, but of course the fat is solid. Here you have to replace the fat by something else. It's terrible. You try inulin and you try all these modern short chain sugars and nutrios and things like that. But they really, these are really challenges. Huh? And this is the question where we have to take into account the interaction with the molecules.
Yeah, great, excellent. Yeah, we have to do it, that just to improve that interaction. Okay, thank you so much, Thomas. It has been a great pleasure. I
No
hope
problem.
that next year we can have you in the building at the BCC.
Oh, with
And,
pleasure. Yeah.
thank you so much. Thank you so much. So interesting.
Thank you very much for inviting me to this quite nice talk. I was really pleased to well, I don't know if it was quite nice. It was quite nice for me to prepare, and I learned a lot again. And so it was. I hope it was useful, and it was a pleasure for me to be with you and your students and your team. Thank you very much indeed.
Excellent. Thank you. Have a
Thank
nice
you.
day. Bye
Have a
bye.
nice day. Bye bye.
Bye bye
Bye bye. Ciao ciao.